In this video, I will introduce you to the P-series test and the integral test. This is a BC only topic. First, let's review the two tests that we already know. For the nth term test, we consider the limit of the rule as n approaches infinity. If that limit equals 0, that actually gives us no information. We have to pick a different test to use. However, if the limit does not equal 0, we can be 100% sure that the series diverges. We also learned about the geometric series test, which of course only applies to a geometric series. So it's going to fit the format a times r to the n power, where a and r are both constants and n is the variable. For the geometric series test, we consider the absolute value of r. If the absolute value of r is less than 1, then the series converges. If the absolute value of r is greater than 1, then the series diverges. If the absolute value of r is equal to 1, use a different test, like the nth term test. Let's look at these three series and determine whether each one converges or diverges. The first one is definitely not a geometric series, so let's try to use the nth term test. Consider the limit of the rule as n approaches infinity. Well, cosine just oscillates back and forth between +1 and -1 as n approaches infinity. So this limit does not exist. The significance of this is that the limit does not equal 0, and we have to mention this for full credit. According to the nth term test, if the limit of the rule as n approaches infinity does not equal 0, the series diverges. So the series diverges by the nth term test, and you must mention the nth term test by name for full credit. When you see a variable as the exponent, it is probably going to be a geometric series. But I would rewrite this a little bit first so we can clearly see a times r to the n power. Quick side lesson, we know that 3 to the a times 3 to the b equals 3 to the a plus b. Flipping that around, if we see 3 to the a plus b, we can rewrite that as 3 to the a times 3 to the b. Or if we saw 3 to the a minus b, we could write that as 3 to the a times 3 to the negative b. But look, that's exactly what we have right here. We can rewrite pi to the n minus 1 power as pi to the n times pi to the -1 power. And then pi to the -1 can go up to the numerator and become 4 pi. So far we have this, but let's put in some parentheses right here and then bring the n outside of the parentheses. Because this fits the geometric form a times r to the n power, we can use the geometric series test. We start by considering the absolute value of r, which in this case is e over pi. We must include the significance of this, which is that e over pi is less than 1. We know this because e is 2 point something and pi is 3 point something. So that's less than 1. Since the absolute value of r is less than 1, the series converges by the geometric series test, which we can abbreviate as GST. This last series is not geometric, so let's go for the nth term test. For the nth term test, we consider the limit of the rule as n approaches infinity, and we can do this in our heads. In the numerator, we only have 2n. In the denominator, we consider which term matters most. As n approaches infinity, that 1 in the front is not going to matter, so we will ignore it. So think of this as 2n divided by -2n. Notice that the n's would cancel, and we would be left with 2 over -2, which equals -1. So that's the limit. For full credit, you must mention the significance, which is that this limit does not equal 0. So the series diverges by the nth term test, and there's no special abbreviation for that, so we just have to write it out. Now I will teach you about a new series called a p-series. A p-series can be written in the form a over n to the p power, where a and p are both constants. Notice that p stands for power, so in a p-series, p will be the power. For example, 2 over n to the third power would be a p-series. Starting with n equals 1, this would be 2 over 1 to the third power plus 2 over 2 to the third power plus 2 over 3 to the third power, etc. That simplifies down to these numbers. Notice we can tell at a glance that this is not geometric. There's no common ratio. There's no number that we can multiply by to get us from one term to the next. From 1 to 8, of course, we are multiplying by 8. But from 8 to 27, not so much. Now I can teach you the p-series test, which of course only applies to a p-series. For the p-series test, we begin by considering the value of p. If p is greater than 1, then the series converges. This is the opposite of what we saw with the geometric series test, but it makes sense because now the p is in the denominator. If p is greater than 1, then the denominator is getting bigger. So the overall value of the fraction is getting smaller. So it sort of makes sense that the series converges. If p is less than 1, then the series diverges. Again, this makes sense because p is in the denominator. If p is less than 1, that means the denominator is getting smaller and smaller and smaller. So the overall value of the fraction is getting bigger and bigger. So it sort of makes sense that the series diverges. The series also diverges when p equals 1. I'm listing this separately because when p equals 1, the series has a special name. It's called a harmonic series. So we could say that a harmonic series always diverges. However, combining these two statements into one, we could say that when p is less than or equal to 1, the series diverges. Again, a harmonic series is a p-series where the p-value is an invisible 1. So it's going to be of the form a over n, where a is a constant. You can simply memorize that a harmonic series always diverges. So what if you run into a series like this, and they ask you, does the series converge or diverge? You can simply say, the series is harmonic, so the series diverges. You don't need a whole proof for this. For the next few examples, let's state whether each series converges or diverges. We need to justify our answer, and let's state the sum if we know how. The fact that n is the exponent means this is probably geometric. Let's rewrite it in the form a times r to the n power. Pulling the 2 out front, we have 2 times 1 over 3 to the n power. But that's the same as 2 times 1/3 to the n power. Since this is geometric, let's use the geometric series test. We begin by considering the absolute value of r, which in this case is 1/3. But it's not enough just to say that the absolute value of r is equal to 1/3. We must mention the significance, which is that 1/3 is less than 1. Don't forget that part. So the series converges by the geometric series test. Make sure you mention GST by name. If a geometric series converges, we can find the sum of the series by dividing the first term by 1 minus r. In this case, the first term is 2 over 3 to the 1 power, so that's 2/3 divided by 1 minus r. This simplifies to 1. The second example is definitely a p-series, so let's use the p-series test. We begin by considering the value of p, which is 3, but that's not enough. We must mention the significance, which is that this is greater than 1. So the series converges by the p-series test, which you can abbreviate PST, and we don't know a formula for the sum of this one. One more time, it makes sense that a p-value greater than 1 will cause the series to converge because the p is in the denominator. So a bigger p makes a bigger denominator, which makes the overall value of the fraction smaller and smaller. So it makes sense that the series converges. For the next two, I encourage you to pause the video and try to do these by yourself. You don't need to find the sum this time. Rewriting 3 over the square root of n as 3 over n to the 1/2 power makes it clear that this is a p-series. So let's use the p-series test. First, we say p is equal to 1/2, which is less than 1. Do not leave off this part. So the series diverges by the p-series test. For the second example, let's split it apart into two separate series. We can also rewrite 1 over 2n squared as 1/4 times 1 over n squared. This makes it more obvious that both series are p-series. For the first series, p equals 2, which is greater than 1, so the series converges by the p-series test. Similarly, for the second series, p equals 3, which is greater than 1, so the series again converges by the p-series test. Since each term of the series converges, the original series also converges. Pause the video and try this example. P equals -7, which is less than 1, so the series diverges by the p-series test. Pause the video and try the next two examples on your own. In this first example, we notice that 8 is 2 to the 3rd power, 27 is 3 to the 3rd power, and 64 is 4 to the 3rd power. With that in mind, we can think of 5 as 5 over 1, and 1 is 1 to the 3rd power. So we can think of this series as the sum of 5 over n to the 3rd power. Clearly a p-series. In this case, p equals 3, which is greater than 1, so the series converges by the p-series test. The second example will be super easy if you recognize that it is a harmonic series. It fits the form a over n. You can simply say series is harmonic, so series diverges. Or, somewhat more awkwardly, you could say p equals 1, which is less than or equal to 1. So the series diverges by the p-series test. Now I'm going to teach you about a new test called the integral test. To see whether a series converges, you can first find out whether a related improper integral converges. As long as f of x eventually satisfies three conditions, either the integral and the series both converge or they both diverge. In order to use the integral test, f of x must eventually be positive, decreasing, and continuous. So what do I mean by eventually? For the first graph, you can see that the entire curve is above the x-axis. So the entire graph is positive. It is also decreasing and continuous. However, looking at the second graph, the entire graph is not positive. Specifically, the green part of the graph is positive, while the red part of the graph is negative. We can say that this graph is eventually positive because the graph is positive from here on. For the integral test, the graph must eventually be continuous, positive, and decreasing. Is this graph decreasing from here on? No, the graph is increasing from 2 to 3, and then it's decreasing from 3 on. So we could use the integral test on a function like this, because we can say that the function is eventually continuous, positive, and decreasing, because in addition to being continuous everywhere, it is positive and decreasing from 3 on. So the integral test says if we have a series with rule f of n, and if f of x is eventually positive, decreasing, and continuous, if the improper integral of f of x converges, then the series converges. If the improper integral of f of x diverges, then the series diverges. Before we use the integral test to determine whether this series converges or diverges, let's think about why we are not going to use any of the other tests that we've learned. In our minds, we can ask ourselves, what happens to the rule as n approaches infinity? And we can see that the denominator is getting bigger and bigger, so therefore the overall value of the fraction is getting smaller and smaller and approaching 0. So the nth term test is out because the rule is approaching 0, which tells us nothing. If we had 1 over 2 to the n, this would be geometric. But we have n squared, so this is not geometric. If this was just 1 over n squared, this would be a p-series. But with the plus 1, this is not a p-series. So we can't use any of the tests that we've learned so far. That's why we're going to use the integral test. For the integral test, we must first identify the f of x, which we will eventually integrate. Take the rule for the series and replace n with x. That's your f of x. Before we move on, we must state that f of x is positive, decreasing, and continuous eventually. We know that this function is always positive because x squared plus 1 is always positive. We know that it is decreasing eventually because as x approaches infinity, the denominator gets bigger and bigger, which means the overall value of the fraction gets smaller and smaller. We also know that f of x is always continuous because the denominator, x squared plus 1, is never 0, so we won't have a vertical asymptote or anything like that. And this is what the graph looks like, a continuous bell curve. Once you have identified f of x and you have established that it meets the 3 criteria, you move on to determining whether or not the improper integral of f of x converges or diverges. The first step is to find the antiderivative of f of x, which we will call capital F of x. And we know that the antiderivative of 1 over x squared plus 1 is the arctangent of x. Next, we find the limit as x approaches the upper limit of capital F of x, and the limit as x approaches the lower limit of capital F of x. Often the easiest way to find the limit of a function is to know what the graph looks like. Let's start with the parent function y equals tangent x, which one period from negative pi over 2 to positive pi over 2 looks like this. Remember that y equals arctangent x is the inverse of y equals tangent x, so the vertical asymptotes at negative pi over 2 and positive pi over 2 become horizontal asymptotes. Also, arctangent has the restriction that it only exists between negative pi over 2 and positive pi over 2, so this is the entire graph. Let's use the graph of arctangent to find the limit as x approaches infinity of capital F of x. As x approaches infinity, arctangent approaches pi over 2, so that's the limit. What about the limit as x approaches 0 of capital F of x? Well, as x approaches 0, arctangent approaches 0, so that is the limit. We could also find the limit as x approaches 0 of arctangent x by direct substitution. Direct substitution gives us arctangent 0, which is the answer to the question, the tangent of what is equal to 0? And we know that the tangent of 0 is equal to 0. So the arctangent of 0 is 0, and that's another way to find the limit. If this problem was just about improper integrals, I would conclude by saying the integral converges to pi over 2 minus 0. That's the upper limit minus the lower limit. However, we are using the integral test to prove whether or not this series converges or diverges. So let's incorporate this statement into our final answer. In summary, we'll say that since the improper integral converges to pi over 2 minus 0, the series converges by the integral test. That was a lot of information, so let's review. We start by determining what f of x is. Then we state that it is positive, decreasing, and continuous eventually. Next, we find the improper integral of f of x by finding the antiderivative, capital F of x. Then we find the upper limit of the antiderivative and the lower limit of the antiderivative. If these are both numbers, then the improper integral converges. It converges to the big number minus the smaller number. So we say, since the improper integral converges to whatever that number is, then the series also converges by the integral test. Of course, if we determine that the improper integral diverges, then the series also diverges by the integral test. Let's see if we can use the integral test to show that this harmonic series diverges. Start by saying f of x, which equals 1 over x, is positive, decreasing, and continuous eventually. We know that these three statements are true because we know that the graph of y equals 1 over x looks like this. So for values of x that are greater than 0, f of x is positive, decreasing, and continuous. In other words, it is eventually positive, decreasing, and continuous. Now we move on to the improper integral part of the problem. The antiderivative of 1 over x is natural log of the absolute value of x. Next, we find the upper limit of the antiderivative and the lower limit of the antiderivative. We know that the graph of y equals natural log x looks like this. So the limit as x approaches infinity does not exist. If one limit does not exist, we already know that the improper integral diverges. So let's incorporate that into the final answer. Since the improper integral diverges, the series diverges by the integral test.